Homework 17, section 7.1, the standard normal curve, video 3. I should mention that we haven't gotten to the standard normal curve yet. We're working our way up to that, and the standard normal curve is the one that we will use throughout the rest of the semester. But let's get back to just a general probability density curve example. This is in the book. It is on page 296. It is, yes, on page 296. It is actually a check your understanding question, so the answers are in the book. We have a probability density curve that doesn't look like the one we saw before. But remember, not all histograms are nice and symmetric, not nice and bell curve. Some of them are skewed to the right, like this one is. So that histogram would transform into a probability density curve that just looks like a quarter pipe if you know about skateboarding. And in this one, we have marks on the x-axis, 1, 2, 3, 4, and 5. And we've got a couple sections underneath the curve labeled. The section between 0 and 1 has an area of 0.63, and the section under the curve between 1 and 2 has an area of 0.23. So let's take a look at some straightforward questions similar to what you will see in your homework. Question A, what is the probability that x is between 0 and 1, or 0 is less than or equal to x is less than or equal to 1? Well, according to the properties of a probability density curve, the answer to that probability would be the same as the area between 0 and 1. And the area between 0 and 1 was given to us as 0.63. So it's the area between 0 and 1, so it's 0.63. So there was nothing to calculate there was just something to observe. Part B, the probability that 1 is less than x is less than 2. Now you may be wondering why in this one did I put less than, but in the previous one I put less than or equal to. It's to make a point. The only difference between the two symbols is that if I put or equal to under it, that just means that we're going to include the value of 1. But as discussed in the previous video, the probability that x equals 1 is 0, because the probability that x equals any single number is always 0. By removing this or equal to part, I'm only removing the number 1 from the values that I'm looking for a probability for. So I've just removed a value whose probability is 0, so it shouldn't affect the overall probability. Same thing with the 2 over here. So the nice thing about these is, in terms of how you do the problem, whether it says less than or it says less than or equal to is irrelevant. So let's get back to part B, the probability that 1 is less than x is less than 2. Using the same property as before, this is the area between 1 and 2. So we just have to go look at our curve, and the area between 1 and 2 is 0.23. What about part C? And again, you'll notice I'm mixing up the less thans versus the less than or equal tos to point out that it's irrelevant. The probability that the probability that 0 is less than x is less than or equal to 2 is equal to, well, again, it's an area. It's the area between 0 and 2. And in this case, it's the sum of these two areas. In fact, you could explicitly say that this is equal to the probability that 0 is less than x is less than or equal to 1, plus the probability that 1 is less than x is less than or equal to 2. Why? Because these are mutually exclusive events. They cannot occur at the same time. I was careful to preserve the correct inequality to the right of the 0 and the correct inequality to the left of the 2. But you'll notice on the ones I used different ones. The main reason I did that was to make sure that these are mutually exclusive. In other words, if your x is between 0 and 1, possibly including 1, then it can't simultaneously be between 1 and 2, excluding the possibility of 1. And the reason making them mutually exclusive is important is because of an OR probability. The probability that x is between 0 and 2 is the probability of this or that. And for mutually exclusive events, that means you can just find the sum of their individual probabilities. So there's two ways to think about how to do this one. The visual is, if I want the total area between 0 and 2, then it's just the sum of the individual areas. More theoretically, it's because this event is this event or this event, and these are mutually exclusive, so we get to add their probabilities. If the visual makes sense, and frankly it should, then you don't have to worry about the theoretical. I guess we should finish the problem though. So 0.63 plus 0.23, which is 0.86. But what about this last one? The probability that x is greater than or equal to 2. Well, we're still looking for an area, but let's think about the area we're looking for. Where on this number line are the numbers that are greater than or equal to 2? Answer, to the right of 2. So we're talking about this portion of the number line down here. Now granted this stops at 5, but there are curves that get closer and closer without touching the x-axis and technically go forever. So we're looking for the area underneath the curve over here. And when I say over here, I mean to the right of 2. So this one's a little bit different because we're looking for the area to the right of 2. And if you'll notice, that area is not labeled with its, we don't know what this area is, or at least it's not labeled yet. So how can we find that? Remember the first property of a probability density curve? That the total area is 1. So we can find this area by subtracting these two from 1. And more generically, the area to the right of a number is 1 minus the area to the left of a number. That will be important real soon. So this is equal to 1 minus the area to the left of 2. And did we not already calculate the area to the left of 2 in question C? So it's 1 minus 0.86. So it looks like it's 0.14, which would make the total area 1 if you checked your addition. So visually speaking, it's just the area to the right. There's also a theoretical approach to this one in terms of complements. What does it mean to be, what's the opposite of being greater than or equal to 2? Being less than 2. And in part C, we found the probability that x was less than 2. I know it says or equal to, but remember, that's irrelevant. And it stops at 0, but there's nothing to the right of 0, to the left of 0. So yeah, the area to the left of 2 was the answer to part C. And remember that the probability of an event is 1 minus the probability of its complement. So the theory backs up the intuition. So to summarize, the area between two numbers represents the probability that x is between those two numbers. The areas are additive as long as the sections don't overlap. And to find the area to the right of something, it's just 1 minus the area to the left of something.